All right, ladies and gentlemen, today we're going to be learning about the life cycle of stars. This will help you a great deal when it comes to teaching the lesson or creating the lesson that you'll be working on. So pay special attention, and as always, please feel free to let me know if you have any questions. So this is a generic picture showing the life cycle of stars, and we're going to go through each step in a moment. So we start with a nebula, and a nebula is a bunch of dust and gas that just kind of hangs out together. And it does that, and it eventually starts getting closer and closer together. It starts condensing. And when it condenses, eventually it starts getting really, really warm. And when it does that, well, I had to show you this first. This is a picture of the Horsehead Nebula. This is one of my favorite pictures. This is a close-up picture of what the Horsehead looks like. To me, it kind of looks like a seahorse. So, and I like seahorses, so I like this one a lot. But when it does start to glow, so remember it's contracting, and it starts to glow, it becomes a protostar. Now, the protostar is not something we can see in the sky at night. It's very, very dim. It hasn't started burning like our sun yet. It's still kind of just a glob of dust and gas that's getting warm. So we call that swirling material a protostar. Now, when the center of that protostar reaches 15 million degrees Celsius, which is 27 million degrees Fahrenheit, that's when nuclear fusion begins. So that's when the star starts to shine, right? Fusion starts, the star achieves what's called hydrostatic equilibrium. Hydrostatic equilibrium is when the same amount of pressure is pushing out that is pushing in. So you've got the same amount pushing out as pushing in, and it reaches this equilibrium state where it doesn't move anymore. It doesn't grow, it doesn't explode, but it doesn't contract on itself anymore. So that's hydrostatic equilibrium. At that point, it becomes what we call a main sequence star. Main sequence stars can be any brightness, they can be any size. What makes them a main sequence star is that they are fusing hydrogen into helium. And they do that for millions to billions of years, depending on their initial mass. So it depends on how much stuff makes them up to begin with. So when you have really, really big stars, there's a bunch of stuff making it up, but it's burning really, really fast, because as it's burning, it has so much mass in there, it just burns very quickly, where something that's really small takes a long time to burn. It'll last literally billions of years. So we'll talk about main sequence stars. They can be anything like blue giants, or they can be the size of our sun, or they can be even smaller. Some of them are the size of Jupiter. In fact, they call Jupiter a failed star. They think it's possible that Jupiter could have formed into a star, but it didn't have quite enough mass to do so. You need a little bit more mass than Jupiter had. If that's the case, we'd have a binary system, which is what most systems are in the entire galaxy that we're aware of. So most stars hang out together. Most stars like to be with friends, but our star, unfortunately, it decided it only wanted to be alone. So how long a star lives and how quickly it dies depends on how much stuff it starts with. So it shows you here this protostar starts with a lot of stuff. It becomes a huge supergiant, and so it immediately becomes a supernova as it dies. But something that's a little bit smaller is going to live a little bit longer. It'll still become a blue supergiant, but it'll have a supernova and it can turn into a black hole. Or you can have something that's our size. Notice we're a lot smaller as our protostar. Here we have a sun-like star. It's relatively small. It's yellow as opposed to blue. And you have a red giant which explodes into what's called a planetary nebula, and we'll talk about that in a second. That then becomes a white dwarf, and that white dwarf can eventually become a black dwarf. And if you look down here, you have even smaller stars, and these smaller stars live for a very, very, very long time, and they don't even turn into anything other than a white dwarf at the end. So let's focus on our medium size and our dwarf size stars for a second. So they start as a main sequence star, they turn into a red giant, That red giant has a nova explosion, not a supernova, just a regular nova. It turns into a white dwarf, and then it eventually turns into a black dwarf. Let's look at each of those steps. The one thing I like about stars is they have a life cycle kind of like we do. So if you look at how a star that our size would be, you consider the nebula and the protostar. That's nothing but the fetus that's inside the womb. It's just kind of starting to be born. Once it's born and it becomes an infant, all the way through its being adulthood, so maybe being 30 or so, it's going to move hydrogen into helium. I'll say maybe 50. Let's say 50 through adulthood. So it goes through that, and then once it's middle age, and I like to think 50 is middle age because of course I'm younger than 50, right? So once it becomes middle age, it turns into this red supergiant. And this red supergiant is living out the end of its life. It starts blowing up, it starts throwing off its layers, and eventually at its old age and its death, it completely blows off its layers in a planetary nebula, so just a regular nova explosion, and it becomes a white dwarf. If it's a really big star, it can become a black hole. Arcturus is an example of a red giant. Arcturus is a fantastic star that you can see in the summer sky. It's also the eye of Taurus, the bull. But when regular stars that are our size die, like I said, it's just a nova explosion. Notice it's still throwing off a lot of layers, but it's not throwing off so many layers that it's going to be something that we can see in our sky during the day. Then after that explosion, the sun shrinks into a white dwarf, and that white dwarf starts burning helium into carbon and eventually can burn carbon into iron, becoming a black dwarf. So this is an example of a white dwarf. Here it looks pretty bright, but they're actually relatively dim. Now let's focus on what happens with a large star, so a giant star, something that starts with a huge amount of mass, something that's going to live a much shorter period of time. This is an example of Betelgeuse. Some people call it Betelgeuse. It depends on where you are in the country, kind of like soda or pop. But it's a red giant. This one is 430 light years away, and it is one of the brightest red giants that we can see in our sky. It's very, very, very red. If you ever get a picture of it, if you ever get to see it in the sky, you can definitely tell that it's a red giant. So when a massive star, let me go back for a second. Betelgeuse is actually a red supergiant, so I misspoke. But when a supergiant does explode, it becomes a supernova. So we're not special, right? We're an average size star, so we just get a nova. But those super big stars, they get to become a supernova. They're lucky that way. And they blow off tons of dust and gas. And that dust and gas, usually that explosion is so bright it can be seen in our star for even during the day. This is the biggest supernova ever recorded. It's 240 million light years away, so it did this 240 million years ago, which is kind of exciting. But this is, like I said, the biggest one ever recorded. This is an image by the Hubble telescope, and keep in mind it is a false color image, so this isn't exactly what it looks like, but it's a very good representation of what, in terms of temperature, what it would look like. Now, after you have a supernova explosion, there's several different things that can happen. One of them is a black hole. And when we were talking about telescopes and we were talking about the electromagnetic spectrum, we talked about how we can find telescopes using X-ray light. So these are the jets. Remember, in this particular image, this area where the red is, that's where all this material is being destroyed. And it's sending out these jets, these huge jets of X-ray light, which allows us to tell, hey, there must be a black hole there. This is what we expect the center of a black hole to look like. It's very, very, very small, smaller than the size of Earth. 20 times or more than the mass of our sun is what's required in order to get a huge black hole. Now, if it doesn't become a black hole, if it's not big enough to become a black hole, it becomes a neutron star. And that neutron star is very, very, very dense. You can see images of a neutron star here. You can barely see it here, but when you look here, it's nice and bright, right? Neutron stars are found more in X-ray images than they are found in visible images. Neutron stars form after a supernova. If they're 3 to 20 times the size that of our sun, they're only 7 to 18 miles across. So you take a star that's 20 times our sun, it explodes, and that core becomes 7 to 18 miles across. That's it. And then the density is twice that of the sun, but it's 1,000,000 times fainter. So if you look at the size of a neutron star, this is Vancouver. This covers most of Vancouver, but that's it. You'd think it would cover at least half of the Earth, but it covers just a very, very, very small area. Now, if the actual if the neutron star starts rotating very, very quickly like this, it turns into what we call a pulsar, and we can recognize pulsars with radio telescopes. They can turn as fast as 3,000 times per second. 3,000 times. That's incredibly fast. And when you hear it on a radio telescope, it sounds something like this. Let's see if we can get it to work. Oh, it's not going to work. That's too bad. I'll play it for you in class, or I'll have another link that'll get it for you. But it sounds just like this ticking sound. And imagine a ticking sound 3,000 times per second. It's absolutely an incredible sound. So this is showing you what happens with a star. All of them start as a nebula. All of them turn into a protostar, but depending on how much dust and gas there is to start with, it can either become a medium star or a dwarf star, or it can become a giant or main sequence star. If it's a medium or dwarf star, it'll turn into a red giant. It'll explode or increase in size by the end of its life. It'll then explode, and again, it's just a nova explosion. It's still a pretty big explosion, but it's just a nova explosion because it's not special enough to get a supernova explosion. It then turns into a white dwarf, which is about the size of the Earth, and after that burns all the helium into carbon, it turns into a black dwarf. However, if you have a lot of dust and gas in that protostar, you're going to get a giant or a main sequence star. That'll eventually turn into a red giant. That red giant will expel its layers. It'll implode on itself, as do red giants. It'll then send off all of its layers into the universe, and it forms a supernova. That supernova then leaves behind the core as either a neutron star, which remember is only 7 to 18 miles across, and that can become a pulsar if it starts rotating really, really fast. You could also get a black hole if the sun is, some say 10 times or more larger than that of our sun. But you get this black hole at that point, and the black hole is even more dense than a neutron star. So the life cycle of a star depends on, and this is very important, depends on its initial mass. So it depends on how much dust and gas there is. And depending on that determines how it's going to live and how it's going to die. So let me know if you have any questions. I'm happy to answer any questions you have about the life cycle of a star. Remember, you're going to be creating a lesson that is going to be taught to earth science students who need to know the basics of this information, not quite as much as you learned here, but they do need to know the basics. And from there, you'll be able to create that part of your lesson. So again, let me know if there's anything you need. I'm always here for you.